The battle report would never fully capture what the German tank commanders witnessed that morning: American Sherman tanks executing maneuvers that defied everything Wehrmacht doctrine said was possible without visual signals. Through the dust and smoke of the North African battlefield, 5 Sherman tanks, separated by broken terrain with no line of sight between them, converged on German positions with timing that seemed supernatural. No flags, no flares, no dispatch riders racing between vehicles. Yet they moved as a single organism, each tank covering blind spots the others couldn't see, each crew knowing exactly where their comrades were positioned. In German Panzer IVs equipped with Fu G5's radios, tank commanders struggled to hear their own company leaders through static that overwhelmed their amplitude modulation systems. The 10-watt German transmitters, state-of-the-art by the 1930s standards, couldn't penetrate more than a few hundred meters when tanks were moving. Most German tanks carried only receivers, unable to report what they saw or call for help. The Americans were operating with technology the Germans didn't know existed: frequency modulation radios in every single tank, crystal-controlled precision, 25 watts of transmission power, and clarity that cut through engine noise and battlefield chaos like a knife through paper. 8,000 miles from Detroit's assembly lines, the most decisive technological advantage of World War II was revealing itself, not in armor thickness or gun caliber, but in the invisible electromagnetic waves that connected every American tank crew in ways the Wehrmacht never imagined possible. The transformation began on July 22, 1941, when the United States Army standardized the Signal Corps radio sets SCR 508, SCR 528, and SCR 538 for all medium tanks. While German forces were advancing through the Soviet Union using tactics that depended on radio communication between command vehicles, American engineers at the Galvin Manufacturing Company, later known as Motorola, were perfecting frequency modulation technology that would render German systems obsolete. The engineering team included Daniel E. Noble, who conceived the application of FM technology in military vehicles, and Henrik Magnoski, the principal RF engineer who solved the technical challenges of installing sophisticated electronics in the harsh environment of a tank. Their creation weighed 181 pounds and transformed every Sherman tank into a node in the world's first battlefield network. The BC604 transmitter generated 25 watts of power, 2.5 times the German FUG-5's output. Operating in the 20.0 to 27.9 MHz frequency range, it provided 10 preset channels with crystal-controlled stability. The dual BC603 receivers in the SCR 508 allowed commanders to monitor multiple frequencies simultaneously, a capability that would prove decisive in combat. The real revolution lay in frequency modulation itself. Edwin Armstrong's FM technology, licensed to the military, eliminated the static and interference that plagued amplitude modulation systems. While German tank radios picked up every electrical discharge as noise, American FM radios delivered clear voice communication even during artillery barrages. November 8, 1942. Operation Torch brought American armor to North Africa. The 2nd Armored Division's tanks landed near Safi and Fadala with SCR 508 radios that would soon demonstrate their superiority over German communications. The Afrika Korps, despite being the Wehrmacht's most experienced armoured force, operated under severe communication limitations. A standard German tank platoon of 5 vehicles included only 1 or 2 with full FUG-5 transceivers capable of both transmitting and receiving. The remaining tanks carried FUG-2 receivers only. They could hear orders but couldn't respond or report enemy positions. German tank platoons functioned through rigid hierarchy. The platoon leader transmitted orders that subordinate tanks acknowledged through actions rather than words. When command tanks were destroyed, easily identified by their multiple antennae, entire platoons lost coordination. This vulnerability would prove catastrophic against American forces, where every tank could assume command functions. The Battle of Kasserine Pass, February 14th to 24th, 1943, provided the first major demonstration of American radio superiority. Though tactically a German victory, the battle revealed capabilities that stunned Wehrmacht observers. During the confused fighting, scattered elements of the U.S. 1st Armored Division maintained coordination across 50 miles of battlefield. Tank crews who had never met coordinated attacks warned each other of threats and called for artillery support through crystal-clear FM communications. German signals intelligence units intercepted American transmissions and noted exceptional clarity and coordination. The 10th Panzer Division's intelligence section reported that American units maintained communication at ranges where German radios produced only static. More disturbing was the realization that every American tank appeared capable of full transmission, not just command vehicles. The German Fu-G5 radios, operating on amplitude modulation in the 27.0 to 33.3 MHz range, suffered from fundamental limitations. The 10-watt transmitter struggled to reach 2 to 3 kilometers in ideal conditions, dropping to mere hundreds of meters when vehicles were moving. Every spark plug firing, every electrical motor, every track movement generated interference that AM systems couldn't filter. September 1943 brought American armor to Italy, where mountainous terrain should have negated radio advantages. Instead, FM technology proved even more valuable in conditions that rendered German AM radios useless. The SCR-508's frequency modulation handled the multipath interference of mountain valleys far better than amplitude modulation. American tanks coordinated movements through terrain where visual signals were impossible and German radios failed completely. During the advance toward Cassino, American armored units demonstrated capabilities that defied German understanding. Tank platoons separated by ridgelines coordinated attacks with precision that German doctrine said required visual contact. The 1st Armored Division's after-action reports described routine coordination at distances where German radios produced only static. June 6, 1944. As Sherman tanks rolled off landing craft at Normandy, their SCR-508 radios maintained contact with naval fire support, coordination impossible with German technology. But the hedgerow fighting revealed a critical gap. Tank radios couldn't communicate with infantry radios operating on different frequencies. The infantry's SCR-300 operated on 40.0 to 48.0 MHz, incompatible with tanks' 20.0 to 27.9 MHz range. This communication gap proved deadly in the bocage, where German infantry with Panzerfausts could approach American tanks while nearby American infantry had no way to warn them. American innovations solved the problem within weeks. Tank crews mounted EE-8 field telephones in ammunition boxes welded to tank exteriors, wired directly to internal communications. By Operation Cobra in late July, this simple modification revolutionized tank infantry cooperation. July 25th to 30th, 1944. Operation Cobra demonstrated the full potential of American radio superiority. The 2nd Armored Division, commanded by Major General Edward H. Brooks, coordinated over 200 Sherman tanks through radio networks that enabled unprecedented battlefield control. German defenders from the Panzer Lehr Division faced an enemy that seemed to possess supernatural awareness. American tanks responded instantly to threats reported by other units miles away. Artillery strikes, coordinated through tank radios, arrived within minutes of target identification. The contrast with German capabilities was stark. Panzer Lehr, once Germany's premier armoured division, had been reduced to communication poverty. Most tanks operated without radios, depending on visual signals in terrain where visibility rarely exceeded 100 metres. The few functioning radios suffered from interference and limited range that prevented effective coordination. The irony was profound. Germany had pioneered radio use in armoured warfare. Heinz Guderian, the architect of Blitzkrieg, had insisted on radio equipment in tanks since the 1920s. His book Achtung Panzer, published in 1937, emphasized communication as essential to armoured operations. Guderian had developed radio communication systems that enabled tank officers to coordinate attacks. He understood that rapid armour advances required reliable communication. Yet by 1943, German tank production couldn't provide the radios Guderian's own doctrine demanded. German production statistics revealed the crisis. In 1943, Germany manufactured approximately 5,700 medium tanks, but fewer than 2,000 Fuji-5 transceivers. Many radios went to command vehicles and assault guns, leaving regular tank units desperately short of communication equipment. Soviet tank forces suffered even worse communication poverty. The T-34, despite being the most produced Allied tank, typically entered combat without any radio equipment. Soviet doctrine relied on flag signals and pre-battle planning, with catastrophic results against German forces in 1941. By 1943, Lend-Lease provided some relief. American radios, including SCR-508 sets, equipped Soviet command tanks. But even by war's end, only about 25% of Soviet tanks carried radios. The comparison highlighted American achievement. While the Soviet Union struggled to equip 1/4 of their tanks with any radios, America achieved 100% deployment of sophisticated FM systems. Motorola's Chicago factory represented American industrial mobilization at its peak. Before the war, the company manufactured car radios. Converting to military production required complete retooling and solving unprecedented technical challenges. Each SCR-508 required 2,748 individual components manufactured to exacting standards. The BC604 transmitter contained 474 capacitors and 385 resistors. Crystal oscillators had to maintain frequency stability despite temperature extremes and combat vibration. Production statistics told the story of American industrial might. 1942, 3,800 SCR-508 family radios. 1943, 11,400 units. 1944, 24,000 units. Total wartime production, over 50,000 tank radio sets. This production miracle ensured that all 49,324 Sherman tanks manufactured during the war received sophisticated radio equipment, an achievement no other nation approached. The SCR-508's advantages went beyond simple frequency modulation. Crystal-controlled frequency stability meant tanks could preset channels before battle and maintain alignment despite combat conditions. German Fuji-5 radios, using variable capacitor tuning, constantly drifted off frequency. The dual receiver configuration allowed commanders to monitor their platoon net and company command net simultaneously. Orders flowed down the chain of command instantly, while commanders maintained awareness of subordinate situations. The BC606 intercom system integrated seamlessly with the radio, allowing all crew members to alert the commander to threats. Throat microphones and noise-cancelling headphones enabled clear communication during combat. Many German tanks lacked intercoms entirely, forcing crews to communicate by touch or shouting. Power management provided another American advantage. The SCR-508 operated on either 12 or 24 volts, automatically adjusting to available power. The dynamotor power supply provided stable, filtered power that eliminated electrical interference. German radios, powered directly from vehicle electrical systems, picked up every spark as static. The tactical advantages of universal radio deployment transformed American armoured doctrine. The combat command structure, flexible task forces organised for specific missions, depended entirely on reliable communications. American commanders could create ad hoc battle groups from different units, confident they could coordinate through compatible radios. This flexibility baffled German commanders accustomed to rigid organizational structures necessitated by limited communications. During the Battle of Araucourt in September 1944, the 4th Armoured Division faced multiple German panzer brigades equipped with superior Panther tanks. The Germans had every advantage in armour and firepower. But American radio coordination proved decisive. Every Sherman could report enemy positions instantly. Tank destroyers received targeting information from tanks they couldn't see. Artillery observers in Sherman command tanks called in devastating barrages within minutes. Over 3 weeks, the 4th Armoured destroyed 281 German armoured vehicles, while losing only 41 Shermans, a 7-to-1 kill ratio that defied technical specifications. Throughout the war, German intelligence failed to grasp the significance of American communication superiority. Combat reports mentioned American coordination, but attributed it to training rather than technology. A captured September 1944 intelligence assessment stated, "American tank units demonstrate good radio discipline and coordination. This appears to result from extensive training and rigid communication procedures." The report completely missed the technological advantage. German tactics never adapted to American capabilities. They continued targeting supposed command tanks based on antenna configurations, not realizing every Sherman could coordinate battlefield responses. They planned ambushes assuming American tanks would lose coordination when separated, not understanding that radio contact maintained unit cohesion regardless of visual contact. March 1945. As American forces approached the Rhine, their communication superiority reached its zenith. The capture of the Remagen Bridge demonstrated the speed of American command and control. When the 9th Armoured Division discovered the Ludendorff Bridge intact, radio reports reached 1st Army headquarters within minutes. Within an hour, divisions across the entire front were shifting to exploit the opportunity. German forces, dependent on telephone lines that American aircraft systematically destroyed, couldn't respond with comparable speed. American radio coordination created an impenetrable defense of the bridgehead. Tank platoons from different battalions integrated seamlessly, coordinating fires through radio networks. German counterattacks, poorly coordinated due to communication failures, arrived piecemeal and were destroyed in detail. April 1945. The encirclement of the Ruhr pocket demonstrated the culmination of American communication superiority. American armoured columns from the 1st and 9th Armies coordinated a complex double envelopment entirely through radio communications. Inside the pocket, 325,000 German troops found themselves trapped, partly because their communications had collapsed. American fighter bombers, guided by radio-equipped forward air controllers, systematically destroyed German communication nodes. Wehrmacht units lost contact with higher headquarters and each other. Field Marshal Walter Model's final messages before communication failure revealed the German plight. No contact with adjacent units. No communication with higher headquarters. Fighting continues, but coordination impossible. American radio superiority profoundly affected the psychological experience of tank warfare. American crews fought with the knowledge they were never alone. Even when physically isolated, they remained connected through radio waves. German tank crews experienced the opposite, profound isolation. Unable to communicate, they fought individual battles within larger engagements. Otto Carius, one of Germany's most successful tank commanders, wrote in his memoir Tigers in the Mud about the challenges of limited communications, though he focused more on tactical aspects than the communication gap itself. The strategic implications extended beyond individual battles. American advances in 1944–45 maintained tempo partly through radio coordination that German forces couldn't match. The Third Army's race across France depended on radio networks that maintained control across hundreds of miles. German commanders consistently underestimated American capabilities because they couldn't conceive of the communication superiority Americans possessed. Heinz Guderian, in his role as Inspector General of Armoured Troops, recognized the problem but couldn't solve it. In a December 1944 memorandum, he acknowledged that American coordination negated German advantages in tank quality. After Germany's surrender, American technical intelligence teams evaluated German equipment. Their findings confirmed what combat experience suggested. German tanks often possessed superior armour and armament, but catastrophically inferior communications. U.S. Army Technical Intelligence Report. Number 176 concluded, German tank communications equipment was approximately 5 years behind American systems. The absence of frequency modulation, limited radio distribution, and poor electrical suppression created critical vulnerabilities. Soviet evaluators reached similar conclusions. The Red Army, given access to captured German equipment, chose to copy American radio designs rather than German systems for post-war development. Production and deployment statistics reveal the magnitude of American achievement. American radio production, SCR 508/5, 28/538 radios produced, 50,000 plus units. Sherman tanks produced 49,324 units. Radio deployment rate 100%. Transmission power 25 watts. Frequency stability crystal controlled plus or minus 0.01%. Range moving 7 miles. Range stationary 10 to 15 miles. German radio production FUG-5 transceivers produced approximately 6,000 units. Medium-heavy tanks produced approximately 12,000 units. Full transceiver deployment rate approximately 20%. Transmission power 10 watts. Frequency stability variable plus or minus 1%. Range moving 0.5 to 1 mile. Range stationary 2 to 3 miles. Communication effectiveness. Average time for American fire mission 3 to 5 minutes. Average time for German fire mission 15 to 30 minutes. American tanks achieving coordination 100%. German tanks with full communication 20%. The radio superiority of Sherman tanks established principles that govern armoured warfare today. Modern main battle tanks carry communication suites that trace their lineage directly to the SCR 508, digital rather than analogue, but fundamentally based on universal deployment and reliable coordination. The German Bundeswehr, rebuilt in the 1950s, prioritised communications based on World War II lessons. Every Leopard tank manufactured has carried comprehensive radio systems. A Bundeswehr training manual explicitly states, "The defeat of superior German tanks by inferior American vehicles with superior radios teaches that. Information dominance outweighs platform superiority." Modern conflicts validate this lesson. In the 1991 Gulf War, coalition forces with superior communications destroyed Iraqi forces equipped with individually superior Soviet-designed tanks but inferior radios. In 2003, American forces again demonstrated that network-centric warfare defeats platform-centric warfare. The story of American Sherman tank radio superiority represents a victory in the electromagnetic spectrum that proved more decisive than advantages in armour or firepower. German tank crews fought their war partially blind to this revolution, discovering too late that every Sherman tank was not just a fighting vehicle, but a node in history's first battlefield network. The SCR 508 radio transformed the M4 Sherman from an adequate medium tank into a component of a weapons system that included every other American tank on the battlefield. This transformation proved more decisive than any improvement in armour or firepower could have achieved. Every Sherman tank carried the tools of victory, not just in its 75mm gun or sloped armour, but in the 181 pounds of radio equipment that connected its crew to every other American tank crew. This connection created a collective intelligence that no individual German tank, regardless of superiority in armour or firepower, could match. German forces discovered this reality through bitter experience. At Kasserine Pass, in Italy's mountains, across France's hedgerows, and in Germany's final battles, American tanks demonstrated coordination that German doctrine said was impossible without visual contact. The Wehrmacht never developed an effective counter because they never fully understood the technological gap. Field Marshal Wilhelm Keitel's reported comment at Germany's surrender, "We knew how to build better tanks, but you knew how to make them work together," captured a fundamental truth, whether accurately quoted or apocryphal. America had built not just 49,324 Sherman tanks, but 49,324 nodes in the world's first armoured battlefield network. The revolution in military affairs that historians identify with modern network-centric warfare actually began in 1942, when the first Sherman tank with an SCR-508 radio entered combat. From that moment, warfare changed forever. The side with superior communications would defeat the side with superior weapons, the network would defeat the platform, and the connected would overcome the isolated. This transformation occurred largely invisible to German forces. They saw American tactical superiority, but didn't recognize its technological foundation until far too late. By the time German commanders understood that every Sherman tank possessed communication capabilities that most German tanks lacked, the war was effectively decided. The German military's failure to recognize and adapt to American communication superiority stands as one of World War II's great intelligence failures. Despite countless battlefield encounters demonstrating American coordination advantages, German leadership never prioritized solving their critical communication weakness. They continued building superior tanks that fought as isolated individuals, while American forces built adequate tanks that fought as coordinated teams. In the end, the electromagnetic waves carried by SCR-508 radios proved more powerful than the armour-piercing rounds fired by German 88mm guns. The ability to coordinate, to share information instantly, to fight as a unified force rather than as individual vehicles. This invisible advantage determined victory more surely than any visible superiority in armour or armament. The Sherman tank's radio superiority changed warfare forever, establishing the principle that in modern combat, connection equals survival and isolation equals defeat. German troops discovered this reality on battlefields across 3 continents, learning too late that the Americans possessed not just numerical superiority, but technological superiority in the dimension that mattered most, the ability to fight as one. July 27, 1944. Near Saint-Denis-le-Gast, Normandy, France. The 88mm shell punched through the Sherman's hull with a metallic shriek that should have spelled death for all 5 crew members inside. A Panther gunner from the 2nd SS Panzer Division Das Reich watched through his sight, waiting for the inevitable eruption of flames that always followed a successful penetration. Target destroyed. Driver, advance 20 meters for better angle on the second tank. But the flames never came. The Sherman's turret traversed toward them, its 76mm gun seeking vengeance. The German loader, already reaching for another round, froze in confusion. That American tank should have been a burning coffin by now. Every training manual, every combat experience from Russia to Africa, every piece of intelligence they possessed said so. What the Panther crew witnessed that morning was a revolution in tank warfare that German forces had completely missed. The M4A376W Sherman they had just engaged was equipped with a wet-stowage ammunition system, double-walled storage bins filled with 38 gallons of fire-suppressant liquid that prevented the catastrophic ammunition fires German gunners had counted on since 1942. This modification, present in every Sherman tank produced after January 1944, had reduced the probability of fire after penetration from 60 to 80% to just 10 to 15%. Across the Norman countryside that morning, 2nd Armoured Division was attacking with 104 of these improved Shermans. Not a single German intelligence report, not one briefing from the Waffenamt, not even whispered rumours from the front had warned German tank crews that their primary tactical assumption about American armour had become dangerously obsolete. The transformation had begun in the aftermath of disaster. February 14, 1943, Kasserine Pass, Tunisia. American armour lay burning across the valley floor, M4 Shermans turned into crematoriums by German 88mm guns. Of 300 American tanks engaged, 183 were destroyed, most consumed by ammunition fires that killed entire crews in seconds. The British Operational Research Section documented that 65% of knocked-out Shermans burned completely. American studies showed even worse figures, up to 80% in some engagements. The Ordnance Department's Tank Automotive Centre analysed every knocked-out Sherman in North Africa. Their conclusion was stark. Ammunition propellant, not gasoline, caused most fires. The 70-plus rounds stored in open racks throughout the fighting compartment became instant incendiaries when struck by hot steel fragments. The solution emerged through iterative design. A chemical engineer from DuPont, attending a tank board meeting in November 1943, suggested surrounding ammunition with liquid. Initial proposals seemed absurd, filling the entire fighting compartment with water, creating submarine-like compartments. But through development, the concept evolved into elegance. Double-walled ammunition containers with liquid-filled cavities positioned in the hull floor away from likely impact points. By December 1943, Pressed Steel Car Company in Pennsylvania was retooling its assembly lines. The first M4A 176W rolled off the production line on January 3, 1944, the W designation standing for wet, though few beyond factory floors understood its significance. Testing at Aberdeen Proving Ground validated the concept beyond expectations. In controlled tests, technicians fired captured German 75mm and 88mm guns at ammunition bins. Dry storage detonated in 73% of hits. Wet storage burned in only 15% of cases. Films of the tests, classified until 1963, showed the dramatic difference. Dry ammunition erupting in pillars of flame versus wet storage producing small puffs of smoke quickly extinguished by spreading liquid. The modification was comprehensive. Each ammunition bin consisted of concentric double-walled cells holding 10 rounds, with the space between walls filled initially with water, then water glycol mixture, and finally a specialized solution called Ammudamp. The chemistry was crucial. Pure water froze in winter. Glycol prevented freezing but caused corrosion, while Ammudamp, ethyl sodium potassium, phosphate, solved both problems while maintaining fire suppression. The M4A 375W carried 100 rounds in floor storage plus 4 ready rounds, protected by 37.1 gallons total. The 76mm variants stored 71 rounds with 36.6 gallons of protection. The system added 900 pounds to tank weight, but dramatically improved survivability. By April 1944, 130 M4A 176W Shermans had arrived in England. The 2nd and 3rd Armoured Divisions each received 52 of these tanks, though initial deployment was delayed. Concerns about training on the new 76mm gun and ammunition supply logistics kept them from the D-Day landings. These improved Shermans would first see combat during Operation Cobra, beginning July 25, 1944. Operation Cobra commenced at 09:38 hours on July 25, 1944, with the heaviest aerial bombardment in tactical support history. As smoke cleared from the carpet bombing, American armour surged forward through the gap at St. Lo. Leading elements included the 2nd and 3rd Armoured Divisions, equipped with the 1st wet-stowage Shermans to see combat in Europe. Panzer Lehr Division, devastated by the bombardment, positioned surviving Panthers in ambush positions. German after-action reports captured when Panzer Lehr's headquarters was overrun reflected growing confusion about American tank resilience. Panthers were achieving penetrations on Shermans at favourable ranges, yet many targets continued fighting or withdrew under their own power rather than burning as expected. The German crews didn't know they had encountered M4A 376W and M4A 176W Shermans from the 67th and 33rd Armoured Regiments. Of the tanks, German gunners believed destroyed, many would return to action within 48 hours after field repairs. Those that burned had typically been struck in the engine compartment. The ammunition protection had worked exactly as designed. German defensive positions, calculated on assumptions of American tank losses, proved inadequate when protected. Shermans survived at unexpected rates. Counterattacks launched, assuming weakened American spearheads met stronger opposition than anticipated. The engineering behind the system represented exceptional wartime innovation. Each storage bin consisted of precisely manufactured double-walled containers with 1.5-inch gaps between inner and outer shells. These gaps contained approximately 0.5 gallons of liquid per 10-round cell. The development process had been remarkably rapid by military standards. Initial water-only systems tested in October 1943 proved the concept, but revealed problems: freezing in cold weather, corrosion of brass cartridge cases, and bacterial growth in stagnant water. Adding ethylene glycol solved freezing but accelerated corrosion. The final solution, Amodamp, contained ethyl sodium potassium phosphate with rust inhibitors and biocides. This mixture remained liquid to -40 degrees Fahrenheit, prevented corrosion, inhibited bacterial growth, and actually improved fire suppression over pure water. Each tank required initial filling, then periodic checking of levels through inspection ports. According to Ordnance Department records, the system's effectiveness exceeded projections. When shell fragments penetrated the bin, liquid would flood out, soaking any exposed propellant before it could ignite. Even if some propellant caught fire, the liquid would prevent spread to other rounds. Tanks went from total loss to minor damage with this single modification. At Kummersdorf Proving Ground, German technical intelligence was conducting analysis of American armour, using specimens captured in Tunisia before wet stowage existed. The evaluation focused on M4A1 tanks from the 1st Armoured Division, captured at Sidi Bou Zid in February 1943. German technical reports meticulously documented every aspect of Sherman design: armour composition, engine performance, transmission characteristics, and ammunition storage. Intelligence bulletins distributed to panzer units contained detailed drawings of ammunition rack placement in sponsons above the track level, with recommendations to target these areas for maximum effect. This intelligence, distributed as doctrine to all panzer units, became standard for German tank crews. Gunnery schools from Putlos to Paderborn taught students to aim for Sherman sponsons. Range cards issued to anti-tank units highlighted these areas in red. The tactical doctrine was embedded so thoroughly that even when sponson hits stopped producing fires, crews assumed they had simply missed the ammunition. The timing proved catastrophic for German forces. Their comprehensive Sherman analysis concluded just as American factories began producing modified variants. Every subsequent intelligence update referenced the older evaluation as definitive. When frontline units reported unusual Sherman survivability, staff officers dismissed these as exaggerations from combat-stressed troops. The transformation of American tank production in early 1944 represented industrial coordination unprecedented in warfare. Fisher Tank Arsenal in Grand Blanc, Michigan, transitioned from M4A2 to M4A3 production, then incorporated the new modifications without stopping the production line. Between February 1944 and March 1945, Fisher produced 3,071 M4A 375W tanks. Hull floors needed complete redesign to accommodate ammunition bins below the turret basket. This meant new stamping dies, modified welding jigs, altered assembly sequences. The partial turret basket, replacing the full rotating floor to allow hull ammunition access, required redesigning the entire turret traverse mechanism. Hydraulic lines, electrical cables, and control linkages all needed rerouting around the new ammunition positions. Pressed Steel Car Company in Pennsylvania achieved similar production milestones. Starting M4A 176W production in January 1944, they manufactured 3,426 units through July 1945. They had to integrate the ammunition system with the new 76mm gun installation, a larger weapon requiring turret modifications, different ammunition, and rebalanced weight distribution. By June 1944, American factories were producing only wet-stowage variants. The transition had been achieved so smoothly that German intelligence, working from year-old captured specimens, remained unaware of the fundamental change. The hedge country of Normandy became an inadvertent testing ground for the modification's effectiveness. The bocage terrain forced combat at ranges where German guns easily penetrated Sherman armour, yet American tank losses proved surprisingly recoverable. Third Army's maintenance battalions reported recovering and repairing 67% of knocked-out Shermans during Operation Cobra. Of tanks that would have been total fire losses with dry storage, approximately 70% returned to service with the new protection. This invisible multiplication of American tank strength confounded German planning at every level. German commanders expressed frustration in war diaries about American tanks appearing to have inexhaustible reserves. Panthers were achieving hits, even penetrations, but many weren't producing permanent kills. American maintenance units were recovering tanks German crews thought destroyed, repairing them and returning them to combat. The mathematical model German staff used for calculating enemy strength, based on permanent losses from ammunition fires, no longer functioned. Major General Maurice Rose's 3rd Armoured Division spearheaded the assault with approximately 200 improved Shermans. In 7 days of intense combat, the division advanced 100 miles, fought dozens of engagements, and maintained operational momentum despite German counterattacks specifically designed to destroy American armour. The German response, Operation Lüttich, the Morton counteroffensive, launched August 7th with 4 panzer divisions aimed at cutting off American spearheads. The plan assumed American armoured units would be exhausted and depleted after their rapid advance. German intelligence estimated American tank strength at 60% of actual numbers, missing the recovered and repaired Shermans that the modification had saved. The 30th Infantry Division's stand at Mortain, supported by tank battalions equipped with modified Shermans, shattered German offensive power. The 743rd Tank Battalion absorbed repeated attacks by SS and Wehrmacht panzer units. Despite suffering numerous penetrations, the battalion maintained cohesion and combat effectiveness throughout the 6-day battle. The Battle of Aracourt in September 1944 provided history's clearest demonstration of the new reality. When the 113th Panzer Brigade attacked American positions on September 19th, they expected to achieve tactical surprise and destroy American armour through superior German gunnery. The initial German attack achieved numerous hits on Shermans of the 4th Armoured Division. Panthers and Panzer IVs reported multiple penetrations on American tanks at favourable ranges, but the American response defied expectations. Instead of withdrawing with heavy losses, the 4th Armoured counterattacked with unexpected strength. The statistics tell the story. The 4th Armoured Division suffered 151 Sherman losses during the Aracourt battles, but of these, only 41 were complete write-offs. The remaining 110 were repaired and returned to service, most within a week. German intelligence, counting all 151 as permanent losses, calculated that 4th Armoured should have been combat ineffective. Instead, it maintained offensive operations throughout. General Patton's initial scepticism about 76mm Shermans reversed after Aracourt. 3rd Army subsequently accepted only 76mm armed wet-stowage variants, recognizing that improved firepower plus enhanced survivability created superior combat capability. As autumn 1944 progressed, second-generation improved Shermans entered combat. The M4A3E8 Easy 8 incorporated lessons learned, improved suspension, wider tracks for better mobility despite the added weight, and refined ammunition storage with better crew access. These tanks began reaching frontline units in October 1944. The specialized assault variant, the M4A3E2 Jumbo, incorporated wet stowage from initial production starting June 1944. With frontal armor reaching 4 inches and turret armor up to 6 inches, the Jumbo could absorb tremendous punishment. Combined with ammunition protection, these tanks achieved survival rates that bewildered German observers. By November 1944, First Army fielded 105 M4A3E2s across various tank battalions. Third Army had 90 Jumbos in 6 battalions. These tanks spearheaded assaults on fortified positions, absorbing punishment that would have destroyed entire companies of earlier Shermans. Operation Watch on Rhine, Germany's last desperate offensive in the West, launched December 16, 1944, based on flawed intelligence about American armoured capabilities. German planning assumed American tank losses would follow patterns established in 1943. The offensive's success depended on rapid destruction of American armoured reserves. German planners calculated that concentrated panzer attacks would eliminate American tank units piecemeal. These calculations assumed traditional Sherman vulnerability. When protected, Sherman survived at unexpected rates. The operational timeline collapsed. SS Obersturmbannführer Joachim Peiper's Kampfgruppe, spearheading 1st SS Panzer Division's attack, encountered this reality near Stoumont on December 19th. His Panthers achieved numerous penetrations on Shermans of the 743rd Tank Battalion at close range, yet American resistance continued. In post-war interrogations, Peiper expressed frustration at American tanks continuing to fight after taking hits that should have destroyed them. The 761st Tank Battalion, the African-American Black Panthers, demonstrated these advantages throughout their 183 days of continuous combat, including the Ardennes fighting. Staff Sergeant Reuben Rivers, posthumously awarded the Medal of Honor, exemplified the survivability provided. His tank absorbed 2 direct hits on November 19th that penetrated the hull, but didn't ignite the ammunition. Rivers continued fighting despite wounds, his crew surviving hits that would have killed them all in earlier Sherman models. As 1945 began, German forces were capturing intact wet stowage Shermans with increasing frequency. Operation Nordwind resulted in the capture of numerous M4 A375W tanks from the 43rd Tank Battalion near Herrlichheim in January. German crews operated these captured vehicles for several days, without recognizing the significance of the liquid-filled ammunition containers. The Waffenamt's Technical Intelligence Branch had effectively ceased functioning by early 1945. The few technical specialists still working focused on desperate wonder weapon projects rather than analyzing enemy equipment. Even if frontline troops had recognized the modification's significance, no mechanism existed to process and disseminate this intelligence. The U.S. Army's Operations Research Office, in their post-war study ORO-T-117, documented the transformation. Pre-modification. Shermans burned in 60 to 80% of penetrating hits. Wet stowage variants burned in only 10 to 15% of cases. This reduction multiplied American armoured effectiveness invisibly. A tank battalion with 50 Shermans suffering 30 penetrating hits would have lost 18 to 24 tanks to fire with dry storage. With wet stowage, only 3 to 5 would burn, leaving 25 to 27 repairable. The battalion maintains combat effectiveness instead of requiring complete reconstitution. Across the European theatre, this mathematical advantage accumulated strategically. Conservative estimates suggest the modification prevented burning in at least 1,000 tanks, representing 5,000 trained crew members saved and dozens of battalions maintaining combat effectiveness. German planning never incorporated these realities. Every operational plan used obsolete data about Sherman vulnerability. This systematic error, repeated across thousands of engagements, contributed directly to German defeat. Post-war interrogations and memoirs confirm the intelligence gap. Not a single German account from the war years mentions recognition of this modification. Otto Carius, who destroyed over 150 enemy tanks, wrote extensively about combat against Shermans in Tigers in the Mud, without mentioning unusual fire resistance. Ernst Bachmann's account of his famous stand never mentions surprise at Sherman's surviving hits. Unit histories compiled by veteran associations provide additional evidence. Histories of Panzer Lehr, 2nd SS Panzer, 116th Panzer Division, contain no recognition of improved Sherman survivability. These are not official histories subject to censorship, but private recollections among comrades. The wet-stowage intelligence failure represents one of the most complete intelligence breakdowns in modern warfare. Multiple factors created this blind spot. German technical evaluation of Sherman tanks occurred using specimens captured before the modification existed. By the time wet-stowage Shermans entered combat, German forces had shifted to defensive operations with limited opportunity for systematic technical intelligence collection. Organizational dysfunction prevented field observations from reaching analysts. German technical intelligence divided between multiple competing agencies with poor information sharing. Resource constraints meant captured vehicles went immediately into service rather than evaluation. Cultural factors, including overconfidence in German technical superiority, reduced perceived need for detailed enemy equipment analysis. The modification's invisibility proved crucial. It didn't change Sherman's appearance, didn't require new tactics, didn't announce its presence. German intelligence, looking for dramatic changes, missed the subtle revolution occurring inside American tanks. The wet-stowage story offers enduring lessons. Technical intelligence requires continuous updating. The enemy studied yesterday may not be the enemy faced today. Innovations need not be revolutionary to be decisive. Evolutionary improvements solving specific problems can prove more valuable than dramatic redesigns. For military engineers, the modification exemplifies effective design philosophy. Identify the specific problem, develop practical solution, implement across production. The modification that can be deployed immediately may trump the perfect solution requiring years of development. Intelligence services see cautionary lessons about analytical blind spots. The enemy capability that seems impossible may be the one that proves decisive. In warfare, where information equals ammunition, intelligence failure proves as deadly as mechanical failure. The Sherman tank wet-stowage ammunition system reduced catastrophic fire probability by 75% and saved thousands of Allied lives. Yet its greatest success was remaining undetected by German forces throughout World War II's crucial final year. From introduction in January 1944 through war's end in May 1945, every major American armoured operation employed substantial numbers of improved Shermans. German forces encountered them from Operation Cobra through the Reich's final defence, capturing and operating hundreds without recognising their fundamental improvement. American engineers designed the system to save lives, not deceive enemies. Yet its invisibility to German intelligence multiplied its effectiveness beyond calculation. The modification validated American design philosophy. Practical solutions implemented quickly proved superior to German pursuit of technical perfection. History records wet-stowage as crucial technical improvement that helped win World War II. More accurately, it should be remembered as the modification that won by remaining hidden, achieving victory through enemy ignorance as much as American engineering. German tank crews fought the wrong enemy with obsolete tactics based on faulty assumptions and lost. The modification didn't just save American lives, it shortened the war by maintaining American armoured strength at levels that accelerated German defeat. In this hidden advantage multiplied across 1,000 battles, we find one of World War II's most remarkable yet unknown stories, a simple modification that changed everything while remaining invisible to those who most needed to see it. March 23, 1945, near Oppenheim on the Rhine River. The scene that unfolded before Wehrmacht artillery spotters defied everything German military doctrine said was possible. Through the morning mist rising from the Rhine's turbulent waters, American vehicles were crossing on what appeared to be a bridge that hadn't existed 12 hours earlier. Not a hastily assembled emergency crossing of planks and boats, but a fully operational bridge capable of supporting 40-ton Sherman tanks. German observers reported the impossible to their commanders. The Americans had constructed a complete treadway bridge across one of Europe's mightiest rivers in darkness, under sporadic artillery fire, in approximately 11 hours. The Wehrmacht's own engineer units, despite being the inheritors of centuries of German military engineering tradition, required a minimum of 48 to 72 hours to construct a comparable crossing under ideal conditions. Most German bridging operations in 1945 took 5 days or more, if they could be completed at all given the chronic shortage of materials and specialized equipment. Yet here were American engineers, working through the night of March 22nd, completing what German doctrine classified as a multi-day operation before the sun had reached its zenith. At German 7th Army headquarters, staff officers struggled to comprehend the reports flooding in from the Rhine's eastern bank. American forces were pouring across at multiple points simultaneously, each crossing supported by different types of bridges that seemed to materialize from nowhere. The transformation had begun 3 years earlier, in 1942, when the United States Army revolutionized military bridging through a combination of mass production, standardized equipment, and radical doctrinal changes that would render German bridging capabilities obsolete. While Wehrmacht engineers still depended on techniques barely changed since World War I, American forces were deploying the M2 treadway bridge, a marvel of military engineering that could be transported on standard trucks and assembled in darkness by men who had never worked together before. Each 12-foot steel treadway section could be maneuvered by 6 men using nothing more than muscle power and simple hand tools. No cranes, no special vehicles, no lengthy preparation required. The engineering revolution was orchestrated by men whose names would never achieve the fame of Patton or Bradley, but whose innovations proved equally decisive. Colonel S.R. Kelly of the Corps of Engineers had overseen the development of the treadway concept at Fort Belvoir, Virginia, transforming theoretical designs into practical military equipment. Major William McKinney had solved the critical problem of how to connect bridge sections in swift water without endangering the engineers. Their solution was elegantly simple: prefabricated steel treadways with integrated flotation, connected by pins that could be inserted even in total darkness by feel alone. The system was so intuitive that engineers from different units, speaking different languages, could work side by side effectively. The Brockway Motor Company of Cortland, New York, had been selected to manufacture the specialized trucks that would carry this revolutionary equipment. Each Brockway model, B6666-ton truck, could transport components for exactly 30 feet of bridge, including steel treadway sections, pneumatic floats, and connecting hardware. The trucks themselves became part of the bridging system, with integrated cranes and winches that eliminated the need for separate heavy equipment. By early 1943, American factories were producing 200 Brockway bridge trucks per month, along with the specialized trailers, boats, and outboard motors that comprised the complete bridging system. December 1943, the Italian campaign provided the first major test of American bridging superiority. At the Volturno River, the 3rd Infantry Division needed to cross 400 feet of swift water under German observation. Wehrmacht intelligence estimated any bridging attempt would require at least 60 hours and be visible from miles away. The 16th Armoured Engineer Battalion accomplished it in 9 hours, working entirely in darkness. The key lay not just in equipment, but in organization. Every American combat engineer battalion included organic bridging companies equipped with standardized equipment. Each company could construct 200 feet of floating bridge independently. When multiple companies worked together, they could span virtually any water obstacle in Europe. The contrast with German capabilities was catastrophic. A standard Wehrmacht infantry division in 1944 possessed one bridging column with equipment that hadn't substantially changed since 1918. The Brückengerät B, Germany's standard military bridge, required specialized vehicles for transport, could only be assembled in daylight and demanded extensively trained personnel. Most critically, the German system required 48 hours minimum to bridge a 300-foot river, and that assumed no enemy interference and perfect conditions. By January 1944, the German High Command's own reports acknowledged that American forces could establish river crossings 5 times faster than Wehrmacht engineers. The Bailey Bridge represented another dimension of American engineering superiority. While the British had invented the Bailey Bridge, American mass production transformed it from a specialized tool into standard equipment. The 15th Engineer Battalion could assemble a 180-foot Bailey Bridge in 4 hours, a task that German engineers, when they had comparable equipment at all, required 2 days to complete. The development of truck-launched Bailey bridges meant that American engineers could begin assembly on one bank and push the completed bridge across the gap without anyone setting foot on the far shore. The 291st Engineer Combat Battalion exemplified American engineering prowess. Commanded by Lieutenant Colonel David Pergrin, the 291st had trained at Camp Swift, Texas, where they practiced assembling bridges blindfolded, in rainstorms, and under simulated artillery fire. Each man could perform every task in the bridging operation. There were no specialists whose absence could halt construction. This redundancy proved critical in combat, where casualties were inevitable. March 7, 1945, the capture of the Ludendorff Bridge at Remagen stunned the German High Command, but what followed proved even more devastating. The 291st Engineer Combat Battalion, working with the 988th and 998th Engineer Treadway Bridge Companies, began constructing an M2 Treadway Bridge on March 9 at 8:30 a.m., about 400 meters downstream from the damaged railroad bridge. Despite constant German artillery fire that caused 35 casualties, including 17 killed or wounded during one barrage that destroyed 19 pontoon floats, they completed the first tactical bridge across the Rhine in 32 hours, finishing at 5:10 p.m. on March 10. Meanwhile, the 51st Engineer Combat Battalion built a 969-foot heavy pontoon bridge upstream between Kripp and Linz in just 27 hours, the fastest floating bridge ever constructed under fire. The speed came from revolutionary preparation and logistics. The 1,139th Engineer Combat Group, supporting Patton's Third Army, maintained forward supply dumps containing complete bridge sets pre-positioned within 5 miles of anticipated crossing sites. Trucks loaded with bridging equipment followed immediately behind advancing armor. When a destroyed bridge was encountered, engineers could begin construction within an hour. The Germans, by contrast, typically required 24 to 48 hours just to bring bridging equipment to a crossing site, assuming they had any available. By 1945, most Wehrmacht units had no bridging capability whatsoever. The American system's greatest advantage lay in its simplicity and standardization. The Engineer Field Manual FM 5-10, Construction and Employment of Fixed and Floating Bridges, established procedures so standardized that engineers from different divisions could work together seamlessly. Every piece of equipment was interchangeable. Every soldier knew the standard procedures. A sergeant from the 249th Engineers could take command of a platoon from the 51st Engineers and continue bridge construction without missing a beat. This interoperability was impossible in the German system, where each unit's equipment and procedures varied. Lieutenant Hans Müller of the German 47th Volksgrenadier Division, captured near Mainz, described his amazement. "We destroyed the bridge at 1600 hours and prepared defensive positions, expecting several days to prepare. By 0400 hours, American tanks were crossing on a new bridge. We didn't understand how this was possible. In the Wehrmacht, such construction required a week of planning and specialized engineer units that no longer existed. Müller's division had lost its organic engineer company in Normandy and never received replacements. Even when German engineers were available, they lacked basic materials." A March 1945 Wehrmacht report noted desperate shortages of lumber, steel, rope, and even nails. The American advantage extended beyond speed to versatility. The M2 Treadway Bridge could be reconfigured as a ferry in 30 minutes, allowing immediate crossing of reconnaissance elements while the bridge was completed. The heavy pontoon bridge could support 70 tons. Loads, accommodating the heaviest Allied equipment. The infantry support bridge could be assembled by combat troops, without engineer assistance. This flexibility meant American commanders could maintain offensive momentum regardless of water obstacles. General Omar Bradley's 12th Army Group had crossed more than 60 major water obstacles between Normandy and the Rhine, each crossing accomplished faster than the last as procedures were refined. The average time to bridge a 200-foot river had dropped from 18 hours in June 1944 to under 4 hours by March 1945. The 1110th Engineer Combat Group's report from March 20, 1945, recorded bridging the main river in 3 hours and 27 minutes, including approach roads. Such speed wasn't exceptional, it had become routine. The industrial miracle behind this capability was staggering. American factories produced 5,800 Brockway bridge trucks, 230,000 pneumatic floats, 14 million square feet of steel treadway, and enough Bailey Bridge components to span 50 miles of river. The Harsco Corporation's plant in Harrisburg, Pennsylvania alone produced 4,000 tons of bridge components monthly. Each component was manufactured to tolerances of 1/16 of an inch, ensuring perfect interchangeability. The training infrastructure matched the industrial effort. The Engineer Replacement Training Center at Fort Belvoir graduated 2,000 bridge specialists monthly. Camp McCain, Mississippi, featured exact replicas of European rivers where entire engineer battalions practiced assault crossings. The 540th Engineer Combat Regiment conducted 147 practice crossings before deploying to Europe. By contrast, German engineer replacements in 1945 often received less than 2 weeks of training, many never seeing actual bridging equipment before reaching the front. The night of March 22 to 23, 1945, exemplified American engineering dominance. While Montgomery's Operation Plunder prepared its elaborate Rhine crossing with weeks of planning and massive artillery preparation, Patton ordered the 5th Infantry Division to cross immediately at Oppenheim. The accompanying engineer units had 6 hours' notice. Working in total darkness, the engineers launched assault boats at 10:30 p.m. By midnight, infantry was securing the far shore. By 4 a.m., a heavy pontoon ferry was operational. By noon on March 23, a complete M2 Treadway Bridge spanned the Rhine. The German response revealed their complete inability to counter American engineering capabilities. Field Marshal Albert Kesselring ordered the Luftwaffe to destroy the Oppenheim Bridge. 42 sorties dropped over 60 tons of bombs. The bridge suffered minor damage, repaired in 2 hours. Even when German aircraft managed to destroy bridge sections, American engineers simply floated replacement sections into position. The 994th Engineer Treadway Bridge Company's war diary noted, "Bridge damaged by enemy action 1430 hours. Repairs complete 1615 hours. Traffic resumed. The systematic superiority extended to every aspect of bridge operations." American bridges featured integrated lighting systems powered by portable generators, allowing night traffic at full speed. German bridges, when they could be built at all,
required vehicles to cross slowly in darkness. American engineers installed anti-mine booms upstream of bridges, deflecting floating explosives. American bridges included telephone lines connecting both banks, coordinating traffic flow. By late March 1945, the Rhine had ceased to be an obstacle for American forces. The 1159th Engineer Combat Group had constructed 6 bridges in 5 days, each capable of handling 1,000 vehicles daily. The entire 9th Army, over 300,000 men with their equipment, crossed in 72 hours. German staff officers, trained to think in terms of week-long river-crossing operations, couldn't adjust their planning to American speed. General Günther Blumentritt, Chief of Staff of the German Western Command, later admitted, "We based our calculations on our own crossing times. The Americans crossed in 1/5 the time we considered physically possible." Captain James Morrison of the 146th Engineer Combat Battalion described the routine that had developed. "We'd get word that a bridge was blown. By the time our reconnaissance arrived, the assault boats were already launching. While infantry secured the far shore, we'd be assembling the bridge. The whole thing became automatic. My men could build a 200-foot treadway in their sleep, and sometimes nearly did. The Germans kept destroying bridges thinking it would delay us. It never worked. Morrison's company built 23 bridges in 30 days. The floating Bailey Bridge combined British design with American mass production to create unprecedented capabilities. The 148th Engineer Combat Battalion assembled a 1,258-foot floating Bailey across the Rhine at Remagen starting March 18th, completing it in less than 36 hours despite constant artillery fire. The bridge used 374 pontoons, 612 Bailey panels, and 14,000 individual components, all fitting together with precision despite being manufactured in dozens of factories across America. The human dimension proved equally decisive. American combat engineers brought practical experience from civilian construction, farming, and manufacturing. Private First Class Angelo Tortorelli of the 291st Engineers had been a construction worker in Newark. Sergeant Robert Knox of the 51st Engineers had built bridges for the Pennsylvania Railroad. These men understood machinery, concrete, and steel in ways that career German soldiers did not. When standard procedures failed, American ingenuity prevailed. The German engineering failure wasn't about courage or skill, but systemic obsolescence. The German Brückengerät B bridging column required 40 specialized vehicles, most of which Germany couldn't produce after 1943. American bridging equipment fit on standard trucks, thousands of which rolled off Detroit assembly lines monthly. German doctrine required extensive reconnaissance and planning. American doctrine emphasized speed over perfection. Colonel Franz Gerhardt, commander of German engineer troops in the Ruhr Pocket, captured in April 1945, testified, "Your bridges appeared faster than we could destroy them. We would blow a bridge, report the crossing blocked, and within hours American vehicles would be crossing. My own engineers required a week to build what yours accomplished overnight. We knew about your equipment superiority, but we didn't understand your organizational superiority. Every American unit seemed capable of building bridges. In the Wehrmacht, only specialized engineers could do this work, and by 1945, most of them were dead or captured." The statistics told the complete story. During the Rhine crossings of March 1945, American engineers constructed 62 bridges totaling over 35,000 feet in length. The average construction time was 8.7 hours. German forces during their 1940 advance into France, at the peak of Wehrmacht capability, had required an average of 73 hours to construct comparable crossings. By 1945, German forces often couldn't build bridges at all, lacking materials, equipment, and trained personnel. The revolution extended beyond bridges to the entire support system. The 331st Engineer General Service Regiment, operated floating maintenance shops that could repair damaged bridge components on site. The 453rd Engineer Depot Company maintained stockpiles of replacement parts within 10 miles of every crossing site. This infrastructure meant that American bridges, once built, stayed operational. German bridges, lacking such support, often became unusable within days. The impact transformed military operations. American armored spearheads advanced, knowing destroyed bridges wouldn't stop them. German defenders couldn't rely on water obstacles for protection. Lieutenant Klaus Weber of the 3rd Panzer Grenadier Division wrote, "The Americans have made rivers meaningless. We blow bridges. They build new ones overnight. It's not warfare as we understand it. They don't fight the river. They simply ignore it." The crossing of the Danube River in April 1945 demonstrated the culmination of American engineering supremacy. The 14th Armored Division needed to cross 1,200 feet of swift water. The attached 13th 1003rd Engineer General Service Regiment accomplished it in 7 hours using standard equipment, building 2 treadway bridges simultaneously from both banks toward the middle. German forces, expecting days to prepare defences, were overrun before they could respond. The industrial foundation deserves emphasis. Bethlehem Steel produced 14,000 tons of bridge components monthly by 1945. Firestone manufactured 400,000 pneumatic floats, each tested to 5,000 pounds of pressure. Evinrude produced 15,000 specialised outboard motors. Equipment failure rates were below 0.1%. German industry, bombed and resource-starved, couldn't maintain existing equipment, much less produce new materials. A captured German report noted only 15% of authorised bridging equipment was available. Master Sergeant Harold Davies of the 234th Engineer Combat Battalion summarised, "The Germans thought rivers would slow us down because rivers slowed them down. They planned their defences assuming we'd need as much time as they did. But we'd turned bridge building into an assembly line operation. Every piece was standardised. Every man knew his job. A destroyed bridge meant a few hours' delay, nothing more." The tactical implications transformed military planning. American commanders could maintain continuous offensive pressure regardless of terrain. German military schools had taught for centuries that rivers were supreme defensive positions. American engineers rendered this doctrine obsolete. Field Marshal Gerd von Rundstedt admitted, "The Americans' ability to cross water obstacles at will was decisive. We could not establish stable defensive lines. Every river we expected to hold for weeks fell in days or hours." Training statistics revealed systematic superiority. American combat engineers received 420 hours of bridging training versus German pioneers' 40 hours in 1945. American engineers practiced night bridging weekly. German doctrine emphasized daylight construction. American units maintained 100% equipment availability. German units reported 30% or less operational. The final Rhine crossings demonstrated total American dominance. On March 24, 1945, during Operation Plunder, the 17th Armoured Engineer Battalion constructed a 1,152-foot treadway bridge at Wesel in 6 hours and 15 minutes, setting a record for the longest floating bridge built under fire. The 275th Engineer Combat Battalion built a 969-foot heavy pontoon bridge at Wallach in 14 hours. German forces could only watch as American engineers turned the Rhine into just another river to cross. By April 1945, American forces crossed every major water obstacle in Germany faster than German forces could retreat across them. The 2nd Armoured Division crossed 8 rivers in 7 days. The 83rd Infantry Division crossed the Rhine, Main, Weser, and Elbe rivers, each crossing accomplished faster than the previous one. German forces, unable to establish defensive positions before Americans arrived, simply disintegrated. General Walter Model's final operational order on April 14, 1945, stated, Enemy bridging capabilities make river lines untenable. Withdraw from water obstacles immediately as they provide no defensive value. This admission from one of Germany's most capable commanders confirmed what American engineers had achieved. They hadn't just built bridges. They had eliminated rivers as military obstacles. The capture of German bridging equipment provided stark comparisons. The German Brückengerät K required 72 hours minimum for a 300-foot span. The American M2 treadway could span the same distance in 6 hours. The technical superiority was overwhelming, but organizational superiority proved even more decisive. Colonel Herbert Mitchell, commander of the 1104th Engineer Combat Group, observed, "The Germans never understood that our speed came from standardization and training, not from some magical technology. Every bridge was built the same way. We didn't need to plan each crossing. We just executed the standard plan faster each time." The human cost differential was telling. American engineer casualties during river crossings averaged 2.3% versus German rates exceeding 15%. American speed meant less exposure to enemy fire. The 541st Engineer Shore Regiment crossed the Rhine with 1,247 men, suffering 11 casualties. The German 47th Engineer Battalion lost 340 of 600 men at the same crossing. Supply statistics for March 1945 illustrated American industrial dominance. Third Army engineers alone consumed 4,000 tons of bridging equipment, 300,000 gallons of fuel, 50 miles of rope and cable, and 2 million board feet of lumber delivered on schedule. German forces received less than 10% of requested engineering supplies. Post-war analysis was revealing. Soviet observers noted American success depended on standardized equipment, universal training, and decentralized execution. The Soviets adopted American bridging equipment wholesale. British forces adopted American deployment techniques. The defeated German army's analysis concluded that American bridging capability had been as decisive as air superiority. General Heinz Guderian, in Soviet captivity, sent a message to former Wehrmacht officers. "The Americans defeated us not through superior courage or tactics, but through superior systems. Their ability to cross rivers at will meant our entire defensive doctrine was obsolete." The legacy extended beyond World War II. The principles established by American combat engineers, rapid deployment, standardized equipment, universal training, and decentralized execution, became the foundation of modern military bridging doctrine worldwide. Field Marshal Wilhelm Keitel's interrogation after Germany's surrender included a telling exchange. When asked about American tactical superiority, he responded, "You could cross rivers as if they weren't there. We would establish a perfect defensive position behind a water obstacle, and within hours American tanks would be crossing. You had eliminated nature itself as our ally. The numbers tell the complete story." American engineers constructed over 3,000 bridges, totaling more than 1 million feet during the European campaign, averaging 11 hours construction time. German forces managed fewer than 400 bridges, averaging over 80 hours. The transformation was complete. Rivers ceased to be obstacles for American forces, while remaining insurmountable barriers for German ones. General Franz Halder, former chief of the German General Staff, writing in 1948, admitted, "The American bridge truck was more decisive than the atomic bomb. The bomb ended the war, but the bridge truck won it. Every calculation we made assumed rivers would delay Allied advances. When this assumption proved false, our entire strategy collapsed." American combat engineers achieved something remarkable. They transformed bridge building from an art into a science, from a specialist capability into a universal skill, from a time-consuming operation into a routine evolution. They turned trucks into bridges, rivers into roads, and obstacles into opportunities. Every American soldier who crossed a river dry-footed, every tank that maintained its advance, every supply truck that reached the front lines, owed their success to engineers who had made the impossible routine. In modern warfare, the ability to overcome obstacles at speed is more important than the ability to create them. The side that can maintain mobility wins. American combat engineers of World War II proved this principle definitively. They turned trucks into bridges overnight, and in doing so, turned the tide of history. German command never knew what hit them. By the time they understood the revolution occurring before their eyes, American tanks were already across the next river, and the war was effectively over. The bridge truck, not the tank or bomber, may have been World War II's most decisive weapon, hidden in plain sight, transforming warfare one river crossing at a time.